Hello everyone, I'm Sarah Hart, I'm the Gresham Professor of Geometry, and welcome to my lecture on where mathematical symbols come from. Now, in 1977, the Voyager space probe was launched, and on that probe there was a golden record. It contained information about our human civilization, the planet Earth, who we are, where we are, and cultural artifacts like music from Bach and other composers, the human voice, and all sorts of wonderful things on this record. There were over 100 pictures as well. The idea was this probe was going to pass through our solar system and then out into wider space, into the galaxy. And one day maybe an alien civilization would find it and they'd want to know who are the people who have created this space probe. Now, one of the important things we wanted to communicate with that was where we are, what we look like, but where we are and what our planet is like. But how do you actually communicate with aliens? They don't know what symbols we use, they don't know how we write, they don't know what it would mean to say we're 93 million miles from our sun. What's a mile? We don't have this common language. So the first job really is to tell the aliens about how we describe numbers. We're going to give them some numbers. And this picture was one of the pictures on the golden record. It was the third picture. And it gives a lot of information about our number systems, lots of symbols. And you can see on that picture how it was described what our numbers are. So to begin with, for the first few numbers, you've got some blobs here. One blob, that's 1. So there's a symbol for 1. 2 is 2. 3 is 3, and so on. What are these vertical and horizontal lines? They are the binary representations of those numbers. So in binary, of course, normally we would use 1s and 0s, but this is our base 2 that computers use. Using 1s and 0s when you're at the same time trying to define 1s and 0s, though, is not a sensible idea, hence the vertical and horizontal lines. So our extraterrestrials looking at this, they've got lots of clues to help them understand what the first few numbers are. So this symbol, what's this? Well, it's the thing that's 5 blobs, so that's what these earthlings must be using for the number 5. Then the numbers carry on, we drop the little blobs after a while, and then you get to the first examples of our place value notation that we use. So this 1 and a 0, that means one lot of 10 and no units, of course, as we know. And there's a couple more examples over in the right-hand side of the picture of that happening for 12 and 24. Then you get an explanation of this exponential notation. So 100 is 10 squared, it's 10 times 10, and so we've got some examples of that. And then what else is defined? Addition, some examples of addition, so that our extraterrestrial friends can understand what we mean by that. We've got some fractions shown and some multiplication. And with those basic building blocks of symbols, then the numbers that are needed to be communicated can be expressed. And units are defined in terms of things that the aliens will know. So the wavelength of light, the size of hydrogen atoms, something like that. We don't write in miles. One thing to mention here, fractions are being used. No decimal points appear on the golden record. I suspect that's because a little dot somewhere could easily be assumed to be, damage to the record or something like that, a flaw in the record. And so that's why fractions are sort of safer to use in this context. Now, why have I shown you this picture? Well, it's to make the point that, our putative alien civilization, it's going to have numbers, it's going to have its own symbols for numbers and for mathematical terms like addition and multiplication. They're different from ours, but the underlying mathematics is, of course, the same, right? We still count 1, 2, 3, 4, 5, 6 in whatever language and whatever symbols we use. So this lecture is about mathematical symbols and notation, but you might very well ask, why does it matter? Surely the underlying mathematics is all going to be the same. And the answer to that is yes, but. The but is that it's people, it's human, conscious beings doing mathematics, and the choice of notation and symbols that we make can actually really influence what mathematics we do. Some notational choices almost prevent us from making progress, inadvertently, while others allow us, they open pathways that we may not have seen before, and they allow us to make more progress. And we'll see examples of that as we go along. But before we do plunge in and start talking about, where our number symbols came from, there's another symbol on this slide that we haven't discussed yet. It's one that seems so fundamental and basic to mathematics that we perhaps haven't even noticed it being used. It's just implicit almost. But this symbol was invented by a man in Tudor Britain. He was born in the little town of Tenby in Wales in about 1510. His name was Robert Record, and he invented the equals sign. And that equals sign, which you might just think it's just part of mathematics, we could never know who could have thought of that. It's just such a basic thing. That was invented, yes, by Robert Record in 1557. And now, when I think about the Voyager space probe, which has left the solar system by now, on that record, in that little piece of machinery out in space, there is a symbol that was invented in Tudor Britain all those years ago and has left our solar system. I love that thought. Lots of these other symbols we'll discuss along the way and their origins. One other thing that we'll talk about as well as we go is, if you like language, or interested in language at all, the language of these mathematical notations and symbols can tell us the path that they have traced through different cultures on our planet. Some things have started, over in India and then moved via the Arab world and come into the Western world. And there's all sorts of wonderful stories that we can find, sort of do a bit of mathematical archaeology to see ideas traveling across the world. And that's a very appealing concept. Okay, so let's get started then and talk about numbers. Now, ever since writing has existed, mathematical writing has existed. This is a Babylonian tablet, sort of Middle Babylonian, about 3,000 years old. And on this tablet, clay tablet, you would write with a stylus making marks. And you can see there are some marks here, and these are numbers. So there's 2 columns of numbers. And this is a bit hard to see on the slide what these symbols actually are, so I've redrawn them and made them a bit bigger. So this is the top half of the tablet, this is the bottom half. There is a reverse as well that takes this table a bit further, but this is enough information already. We can see this first column. If you just sort of, with a bit of detective work, we can see this looks like 1, 2, 3. You've got 3 marks, 4 marks, 5 marks, and so on and so on. This seems to be just the numbers, 1, 2, 3, 4, 5, and so on. It gets a bit hard by the time you get to something like 7. You have to be perhaps starting to count the number of little marks, so maybe that's not quite efficient. And then we get 8, 9. Oh, and then there's something different. And that's something different. If we think about, fingers, 1, 2, 3, 4. By the time we have 10 fingers, that's 2 hands. And so probably this symbol here is kind of looking like 2 hands together because it's 10 fingers. So that's 10. And then we carry on 11, 12, and so on. That's all very nice. What about the second column? What is being recorded there? Well, we can count up here, there are 9 little wedges. So 1 corresponds to 9. And 2, what's this? It's a 10. And then there's 8 little wedges. So 10 and 8, 18. So 2 goes with 18. If you look at the next one, 3, that looks like 27. 4, 36. This is the 9 times table, written on a 3,000-year-old tablet. The 9 times table. It's all great. And now we can see at the bottom of this column here, and we see something that is telling us about the Babylonian method of writing numbers, because this is 4 wedge shapes. But it's not the number, can't be the number 4. From context, it ought to be 7 times 9, which is 63. And that's what it is. The Babylonians used a base 60 mathematical writing system. So we have a base 10 system. We write tens and hundreds and powers of 10 like that. They had 60s. So this means 60, then they leave a little space, and then 3. So it means 63, which is what it ought to mean from the context. So this is a quite efficient way of writing, but there are some problems with it. One problem is, how do you just write the number 60? Because you can't leave a space because there's nothing else that goes after it. So if you just see a wedge on its own, you have to kind of work out from context whether that's the number 1 or the number 60. So this is sort of problematic with this system. However, it was a useful system and lasted a long time. Let's look at another 1 or 2 early number systems. So what were the ancient Egyptians doing? Well, they didn't have to worry about, can I see a space or is there a space, what's going on? Because they had a symbol for every power of 10. And then you just have as many of those as you needed. So here are some of the symbols. And here's an example there on the slide. At the top you can see 1 lotus flower, that's 1,000. 2 coiled ropes, 200. 3 bent sticks, that's 30. And 4 straight sticks, that's 4. So that's number there is 1,234. Because there was a different symbol for each power of 10, you didn't have to worry about leaving spaces or things. There wasn't an ambiguity between, so the next 2 ancient Egyptian numbers here. You've got 4 pointing fingers, that's 40,000. And then you haven't got any 1,000s, but you've got some hundreds. There are 9 coiled ropes there, if I've done it right. So that's 40,905, right? You don't have to worry about the missing thousands because you just don't see a lotus flower symbol, so there aren't any. The number on the bottom, completely obviously a different number, that has got 495. So they can't be confused, you have different symbols. This is, again, it's an okay solution, but it's quite unwieldy for big numbers, and you do have to often stop and count how many of each little symbol there are. So that's the ancient Egyptian system. There were lots of different systems, I'm just mentioning a few. The ancient Chinese system had powers of 10, but it solved the problem of counting lots of little symbols by also incorporating a different symbol for each number 1 to 9. So if you wanted 400, you'd write your symbol for 4 and then your symbol for 100. Ancient Greece. Now, this wasn't quite the first system they developed, but this alphabetic system was quite an ingenious way of writing, at least for small numbers. It was efficient because there was a number from 1 up to 9. They were just the first 9 digits of the Greek alphabet, or actually an early version of it, because there's this digamma is in between epsilon, between eta and zeta. And so you've got alpha is 1, beta is 2, gamma is 3, and so on. But then, once you get up to 10, you then have numbers 10, 20, 30, 40, 50, 60, up to 90 are the next letters of the Greek alphabet. And then you have symbols again carrying on for 100, 200, and so on. So you can write 444 with, what's that, upsilon and mu and delta. So mu is 40 and delta is 4. Now, that worked, as I say, it's reasonably efficient for small numbers, but what are you going to do when you want to write, 1,073? It's tricky, and you run out of letters. I mean, even with these couple of extra letters that were dropped from the Greek alphabet at various points, you start to run out of letters. So that's sort of problematic as well. Why didn't they realise, instead of writing mu for 40 and delta for 4, why can't we just, have a place system like the Babylonians had started to do, and just have, just a delta meaning 4, and then you can put things in different places. Well, one reason, the ancient Greeks were not stupid. They were doing great mathematics. It wasn't that they weren't able to think of this. I guess it's more that they weren't using the written numbers to do calculations in the way we do now. Somehow they didn't need to develop that technology yet because they were using counting boards. Just like the Romans were as well, they had counting boards, or they'd have an abacus. So we do have some kind of archaeological evidence for what they were doing. There's a tablet called the Salamis tablet, which survives, and there are columns for different denominations, I guess, of numbers. So the biggest one you would have would be talents, and then minae, drachmas, obols, so 6 obols and a drachma, and then you'd have fractions of obols. So that survives. But we also have references in writing to how these things were used. So you have these, little stones that you'd move around on the counting board, and they would have different values depending which column they were in. So Polybius, 2nd century BC or thereabouts, he's got this thing, he says, the courtiers who surround kings are exactly like the counters on the lines of a counting board, for depending on the will of the reckoner, they may be valued either at no more than a mere chalkos, which is, I think, an eighth of an obol, it's a very small amount, or else at a whole talent. So actually the difference in those, it's something like 288,000 times as much value if you're a talent compared. And so, he's giving this description, everyone knows what he means because everyone knows about counting boards. It's the same in Rome. Nobody is actually doing arithmetic. Nobody's trying to do multiplication with Roman numerals. They are doing the calculations on the counting board with their little stones, and the Latin for that is calculi, hence the word calculate, and also calculus. They're moving them around. They are not trying to work out how to multiply MDXCVII by XVL or something. They're not trying to do that. So they aren't needing to grapple with this. They also had expressions that tell us that they're using these things. So they had an expression, vocare aliquem ad calculos, which is meaning to settle up with someone, to kind of pay your debts, but what it literally means is to call someone to the calculating table or the counting board. So this is what they were doing, and so they were not held back in that sense by the cumbersome numbers, although they were a bit, as we'll see, it took longer to develop various technologies because of it. Okay, so those are kind of some of the old number systems. What about our numbers that we now use? Where did they come from? So they were developed in India. We don't know exact dates, we don't know for sure. There are various manuscripts that are found that are hard to date. The manuscripts themselves may be older than the writing that's on them. But what we do think happened is that there was an early Brahmi number system that originally would have had the numbers for 1 to 9 and then probably 10, 20, 30 and so on. But at some point those later ones were dropped and we just kept the symbols for 1 to 9. And then crucially, getting round the problem faced by the early Babylonians, although they did invent a placeholder symbol at some point in the first few centuries AD, and I'm not confident as to when because no one is, this happened. So a little dot started to be used for a placeholder. So, if you want to write 105 and you want to distinguish that from writing 15, you have to say there's no tens happening. So if on your counting board, that's fine, you can just leave a gap. But if you're writing it down, you need to signify that in some way, otherwise things get confusing. And this is what they did. They put a little dot, and that became our 0. So to begin with, it was just a placeholder. It wasn't a number in the same way that we've got numbers that people were considering them. However, it later did start to become treated as a number in its own right. So you have people like Brahmagupta, the Indian mathematician, around 730 AD, was giving rules for dealing with 0. So he, for example, said, any number subtracted from itself gives you 0. So this is the first beginnings of it being treated as a number like other numbers. It took a long time for that to happen. So the title of this slide has got Arabic crossed out and Indian written in for Indian numerals. These are Indian numbers. So why do we call them Arabic numbers? Well, it's because they didn't come straight to us from India. What happened was that Arabic mathematicians like Al-Khwarizmi in the 9th century had translations from the Sanskrit text into Arabic of various mathematical works, including works by Brahmagupta. And Al-Khwarizmi found out about these symbols and about how they were being used in calculation as well. It's not just the symbols, it's a new method of calculation that can be done that doesn't require counting boards or an abacus. So these symbols were brought into Arab mathematics at about this time, and Al-Khwarizmi wrote about them. He wrote a book about these new symbols and the Hindu mathematics. He's known to us as well because he also wrote about how to solve problems that involved what we now call algebra. And this word here that features in the title of one of his books, al-jabr, is this is where we get our word algebra from. And Al-Khwarizmi's name himself, that has become our word algorithm. So he's very influential for mathematics in general and Western mathematics in particular. So he is working on these things, and he's seeing the new Indian numerals, he's got them into Arabic, and from there, not directly, I think, from his work, but from the Arab world and from our interactions, so traders and merchants that are working in Italy and places like that are traveling and meeting along trade routes. They're talking to Arab traders and they are learning about these new numbers that are really efficient and you can do calculations with them, and they are a great new piece of technology that are going to supplant the abacus and the counting board. It's really through trade that these pieces of technology are transmitted. Al-Khwarizmi's work was translated into Latin. It was seen in the West actually a lot earlier than when the numbers really caught on, but it really was through trade routes that these numbers spread. And one of the people who was spreading them was this chap, Leonardo of Pisa, who is better known as Fibonacci. And his father was a merchant. He learnt about these new numbers and about how you can express any number in terms of them and how you can calculate with them directly without using any kind of board or abacus. And he wrote about them in a book called Liber Abaci in 1202. I've quoted from it here. You don't need to be able to speak Latin to get the gist of this, but he's saying, here are the 9 Indian figures, the 9 figures of the Indians, and he writes them down, 987654321. But I like, these are written probably as they would have been seen in an Arabic book, because of course in Arabic you read from right to left, and so that they would be in ascending order then. He's preserved that way of writing, even though it's a little bit counterintuitive to write them in descending order, but that must be why he did it, just sort of without thinking about it. So he's written down these 9 numbers, but just notice, he says with these 9 figures and with this sign, 0. So it's not a number like the others, it's a different thing. You've got the 9 figures and this sign 0, which the Arabs call zephyr. So zephyr, that gives us our word cipher. That's an old word for 0. And from cipher we get ciphering, which is an old word for kind of doing arithmetic or calculations. So with these 9 figures and the sign 0, which the Arabs call zephyr, we can write whatever number we like. And then he gives some examples of how to do that. So this is, here it is happening. Now, these amazing numbers, which allow you to do calculations by writing them down and without using, little stones, we're not using our calculi to calculate, we're using our cipher to do ciphering, or algorithmus is another word for this new way of calculating. They spread, but it took a while for them to, it wasn't just like everyone said, oh yes, this is good, we're going to immediately adopt this. There was resistance, it took a long time. If you are happy and your friend is happy and you trust each other that you've got your financial calculations are done in the way that you're familiar with the symbols you're familiar with, it takes a while for that trust to be gained for a new system. So it did take time, and we have instances like in 1299, the Florence City Council banned writing things in these Indian Arabic numbers in financial records. You had to write it out in words. The worry was not that they didn't think they expressed numbers, but that it was too easy to tamper with them potentially. You could turn this weird 0 thing into a 6 or a 9 just by adding a little tail or a hook. And so, potentially you could tamper with financial records. So you had to write things out in full in words, just as, on the rare occasions nowadays where we write a check, you do that exact thing for that same reason, that you want a clearer record of what these things are. So, those numbers took a while to be accepted. There are various woodcuts and books published about using this new system, how to do ciphering. Here is arithmetic personified. She's sort of disdainfully looking away from the counting board, and she's pointing to the wonderful new Indian Arabic numbers here. This is the way forward. There they are, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 and 100 and 200 and so on. This is the new system. And it did catch on, but it took a while. And particularly we could say that, or notice that this 0, you saw when Fibonacci introduced it, it was 9 figures and this weird 0 thing. 0 really was treated with suspicion, with caution for an awfully long time. Centuries, really. Even by Shakespeare's time, you've got in King Lear, there's a scene where King Lear, has been brought low, and his fool is taunting him, and he's saying, thou art an O without a figure. So you're nothing or worthless. You're an O or 0 with no figure attached. You haven't got a number attached to you, so you don't mean anything. If there's a number attached to a 0, then it might turn 1 into 10, but on its own, it's nothing. I mean, that's okay, that's true, but it's the point that he's saying you're without a figure. So the 0 somehow isn't a figure. It's not a number like the others. And so this view persisted for a long time. And we see that even when people are talking about trying to solve algebraical problems, still for a long time, even when they're doing quite complicated algebra that requires the use of things like even the square root of negative numbers, which is a difficult concept, even when they're doing that, they're still not happy about 0, and they're still not happy even about negative numbers. So it really takes a long time for these things to get acceptance. So we've seen where our numbers come from and how this new technology helped our number symbols to be adopted. But there, of course, are lots of other mathematical symbols, algebraical symbols, the plus sign and things like this. We've mentioned the equal sign, and we'll talk about Robert Record a bit more in due course. But let's have a little tour of algebra. Now, the beginnings of algebra were what is called rhetorical algebra. Everything was expressed in words. And this is true, the Babylonians, they had things that we might now call algebraic problems. And it would be, I have a length and a width, and the length and the width add together to make this number, and the length and the width, the difference between the length and the width is this other number, find the length and the width. So it was all done in words. This is a particularly beautiful example. So in India, the tradition was for Sanskrit writing to be done in poetry. So you have lots of people who are mathematicians and poets and astronomers. It's all part of the same intellectual thing, really. This is a beautiful problem. This is by Bhaskara in a book that he dedicated to his daughter Lilavati in the 12th century. And wouldn't it be lovely if our algebra problems were like this? So it's about a swarm of bees, and a fifth part of them comes to rest on one flower, and then 3 times the difference between that and the third of it flew to another flower, and then there's one bee alone remained in the air, attracted by the perfume of a jasmine and a bloom. Tell me, beautiful girl, how many bees were in the swarm? So this is a very poetic description of a problem that it's all in words, and the solution is given also in words. So this, yes, it's algebra, but there are no symbols yet involved. So it's not symbolic algebra, it's rhetorical algebra. Now there's an intermediate step, which is where you start to maybe use a few abbreviations in what you're doing. And that's got the very jazzy name of syncopated algebra. And that's a kind of an intermediate step, which is not, it's not purely abstract, but we're somewhere along the way. And an example of this is in the work of Diophantus. So he was a Greek mathematician working in Ish, the 3rd century AD, and he wrote a very influential book called Arithmetica, which you may happen to know that it was in Fermat's copy of Arithmetica that he wrote that famous marginal note about having a wonderful theorem, and the margin is too small to contain it. So, Arithmetica was used for a long time. It's really a great achievement of early mathematics. He did use some abbreviations, maybe 1 or 2 symbols. He had a symbol for minus, I believe, but it was basically words with some abbreviations. And there's a problem about that if you're writing in Greek, in ancient Greek, because we've seen that the symbols for numbers were just letters of the alphabet. So alpha is 1, beta is 2, and so on. So if you then want to start using symbols for variables, or letters for variables like we would now, that's going to be problematic. Example, he was looking at problems about the squares and the cubes of things, all very geometrically based. So a square, x squared, which he wouldn't have written, you think of it as a square of side x, and something cubed is a cube of side that thing. So it's all kind of couched in geometry, but there is some algebra happening. It's still all in words. If you want to write a symbol, an abbreviation for cube, the cube of something, well, the word is kubos, and the first letter of kubos is kappa, but kappa is the number 20. So that's going to be very confusing, because if you look at it, you won't know whether it's 20 or it's the cube. So then what do you do? Well, maybe use the first 2 letters, kappa, upsilon, and then that's problematic because that actually represents the number 20,400. So you can see this is really difficult. And somehow all of these things are cut from the same cloth. They are all using letters, alphabet letters, which also mean numbers, and now they also have to mean something else as well. It's very difficult to sort of parse an expression like that. And this helps to explain why it didn't really catch on kind of using symbols, because the symbols were having to do too much work, the same symbols. What eventually seemed to have happened is that you have an expression, a little thing like this, which is kappa, and then sort of a superscript, little upsilon on the top, and that's your abbreviation for the kubos, or cube. So, because of all these issues around this, and abbreviations perhaps not really helping you much more than just writing in words, writing your mathematics and your algebra in words persisted and carried on for at least the next 1,000 years. And the sort of beginnings of progress on this are in Renaissance Italy, where you've got people like Cardano. So he's very famous. He's written a book called Ars Magna, and in that book he explains how to solve any cubic equation. So, we at school, we learn the quadratic formula for solving quadratic equations, things with x squareds in them, basically. The cubic equation is a bit harder to solve, But it was worked out at around this time. There were partial solutions given by others and lots of arguing about who'd come up with what first. But Cardano did put how to solve any cubic in this book, Ars Magna of 1545. Now, it's a great achievement. And it's even more of a great achievement when you realise he doesn't like 0, he doesn't like negative numbers. And because of that, it wasn't just one cubic equation. So if we were nowadays, when we try and solve, a quadratic equation, what we do is our first step before anything else, we bring everything over to the left-hand side and equals 0 on the right. Well, the equal sign hadn't been invented yet. He didn't like 0, and he didn't like any negative numbers. So you can't do that. You're not even writing down equations at all. You're saying in words that things are equal to other things. So just an example here I've written that something like, an expression like, again, not the notation that would be used, but something like x squared plus ax, the number plus some multiple of its root is a constant. That's viewed as a different kind of thing. It's a different kind of problem to solve from something that looks like the number is equal to some multiple of its root plus another number. They were thought and classified as different things. And with cubic equations, you can imagine there's many more different subtypes of cubic. So this made for much longer descriptions of how to solve all of these things, but it was done, in spite of the suspicion around even 0 and negative numbers. Never mind imaginary numbers like the square root of -1. Geometrical arguments were largely what were being used, and Cardano then that made it very difficult to do anything with equations where you might have higher powers, like something to the power 4, because that doesn't make, there's no fourth dimension, of course. Now we suspect that there might be, but more importantly, we don't insist that anything involving a fourth power somehow has to be corresponding to a geometrical thing. We think differently nowadays. So this terminology and the kind of the mindset, amazing though the achievement was, there are ways in which we hadn't seen further at that stage. So the next steps, really, we start to get, there's one or two symbols, but really they're really coming from abbreviations. The next steps, really, I would say, are coming in Germany in the later part of the 16th century, where you have writers like Michael Stiefel and Christoph Rudolph, and so this word cos got there, and the Cossic art. So the Italian word for unknown is cosa, and that became cos. So Rudolph's book, De Cos, is about finding the unknown, like doing algebra. And in England, this was called the Cossic art often. So Michael Stiefel, here he is, he was the first to use in print the symbols plus and minus for addition and subtraction. As you can see there, before then, you'd get expressions like this one. So what's this thing? This looks very difficult for us to read. Again, the problem is everything looks the same somehow, well, except we now at least have different symbols for the numbers, so they're easy to pick out. So this is one lot of the zensus, that's the number, the unknown that we're trying to find. Pu plus, P for plus. 5 lots of R. What's R? It's the radix, the root. So this is the root of the zensus that we're trying to find. Already implicit in this is that there is a root, and this is sort of assumed to be a positive number. And so we are, with the notation, we're accidentally not allowing ourselves really to consider other possibilities, like quadratic equations have 2 roots usually. M minus 6. So that's what things were looking like to begin with. Then a few years later, you get different editions of books, and the notation gradually changes with the different editions of De Cos, for example. Then, within a few years, that expression would become something like this. So 1 lot of Q, the square, plus 5 lots of N, the number, minus 6. So that's, to our modern eyes, much easier to read. And I think, to everyone's eyes, because you're starting to just get different things. The operations are symbols. You can spot what they are. You can see what the numbers are. We don't yet, though, it's not easy to just see by glancing at this that Q and N are related in any way. So that it doesn't help our intuition. So the final kind of step in this progression is that we start to see explicitly, look, here is an A, and here is A times A. And that's that number. It's one single number, and it's there, but it's also over here squared. So it makes it much easier it doesn't sort of get rid of, at the starting gates, the possibility that A might be, negative or something like this, or even imaginary. This is a better notation in the sense that it's more amenable to generalization and abstraction. So there was some good progress here. I will just say before moving on, another bit of development that happened in Germany at this time was with square roots. So the square root symbol was coming in around this time, and it appeared, I believe, first in Germany as modern square root system. But the notation for cube roots was terrible. Let's see if we can see it on the slide. So the cube root symbol, you take your square root, but because it's cube root and cube is 3, you have 3 little wiggles. Very hard to see in a handwritten text. And then, okay, the fourth root, does that have 4 little wiggles? No, it does not. It has 2 little wiggles. Why? Because it's the square root of the square root. So this is very confusing. And, if you get to something like the 12th root, well, that's the cube root of the square root of the square root. So is that going to have 5 wiggles? And then what's the 5th root going to have? It's just impossible. And, it totally prevents you from being able to talk about, the nth root of anything. You just can't do it. You just have to, how many wiggles am I going to write? So something like this, they stop progress being made, whereas the good notation allows progress to be made. And we're going to see that now with the start of something which later becomes an exponent notation. So thing x to the 5 or something like that. So kind of a precursor of this was Bombelli in 1579. So what's he writing here? Well, we saw when we start to be able to have, A and A times A and A times A times A. Of course, being humans, we would very soon start to say, how many A's have I got, and can I just write that down as a number? And this is what Bombelli is doing. Unfortunately, the notation sort of obscures what the unknown is. It's hidden a little bit. So he's got lots of expressions like this in his book, a whole page full of examples, really, of how this thing works. And what is this thing? He's not saying 4 plus 7 is 11. It's not that. That little kind of curved line underneath, that's representing the unknown. So what he's actually saying, we'd now write it as x to the 4 times x to the 7 equals x to the 11. He's introducing the fact that we know about powers now, that when you multiply powers, you add those coefficients together. So he gives lots of examples of this, but the issue here is that, it doesn't allow for you to do things that you might later want to do. It's not his fault. He did the trick for what he wanted to do, but it's difficult then. You've got this unknown that you haven't got a letter for, and so what if you wanted to have 2 unknowns or something? What if you wanted to talk about something like a graph that we talk about now, y equals x squared, the parabola graph that we perhaps drew at one point in our lives? You can't do that with this notation. But happily, Descartes comes along in his book Geometry in 1637, and he introduces and gives us the exponent notation that we use today. And actually this book, it's in French, it's not in Latin, it's in French. The mathematical expressions really do look quite modern. They look like how we might write things now mostly. So he's got things like, he defines the a squared as a times a cubed, a times a times a, and so on to infinity. You can carry this on as long as you like. Another really crucial thing about this book is he's stepping away from the idea that, something cubed has to involve an actual cube in 3 dimensions. Instead, he talks about curves that are, they're 2-dimensional things often, and you express them in terms of relationships between 2 variables. So that y equals x squared, not how he would write it, but that kind of relationship between 2 variables that you can plot on the plane allows you to move away, and so then there's nothing to stop you writing y equals x to the 5, and looking at that. You don't have to be thinking it's all 5-dimensional or something, and then dismissing it as being beyond nature, as Cardano would have done. So, there's a lot to talk about in this book, but he gives us the exponent notation. Another thing he gives us is the convention of having variables being at the end of the alphabet. So x, y, z, those are variables, and constants terms being at the start of the alphabet, a, b, and c. So, when we did the quadratic formula in school, we learned how to solve ax squared plus bx plus c equals 0. That convention is from Descartes. Now, the idea of viewing curves as sort of dynamic things that were expressing relationships between your y and your x or other variables, and somehow they're moving, and then you could have a rate of change of them. That is what laid the groundwork really for calculus to come into existence. Now, I'm not going to talk about calculus really. I'll give you 1 minute just to show you some notation. And Newton and Leibniz, of course, battled it out over who had priority, who had come up with the idea first. The notation that comes from the sort of Newtonian outlook is not, in my view, as good as the notation that comes from the Leibnizian outlook. So if you're trying to do what Newton might have written, so this dot means you differentiate once. Don't worry if you don't know what that is, we're moving on in a moment. 2 dots mean you do it twice, and so if you want to do it 8 times, you just have to have, a horrible panoply of dots above your x, and you have to count how many there are, and you can miss some with an ink spot or something. So this becomes unwieldy. Whereas this notation that we sort of developed from what Leibniz was doing, where it looks like fractions, that actually it fits in well with how differentiation and its reverse integration seem to work, so that's good. And you can then see immediately how many times you're doing this process. So there's an 8, do it 8 times. That's much more easy to see than the 8 dots. And you can also give yourself the latitude to do it n times if you want to. So many people would take the view, and I'm one of them, that this kind of Leibnizian notation is superior. Although there are places for the other. So, we've seen how the development of certain notations can allow new ideas to emerge, and they're helpful, they're sort of a seedbed for new concepts. Once you have the concept of x to the n, well, n has been a positive whole number, a positive integer, x squared, and so on, but could you have x to a non-whole number power? Could you have x to the a half, maybe? Could you raise it to some other power that isn't a whole number? Well, if you remember that, take an x, the square root of x times the square root of x equals x. So the square root of x squared equals x. And since we know about the addition rule of exponents, maybe we start to use the notation x to the power a half for the square root. So you can make these you can generalize a bit and start to use this notation more broadly. And of course, understanding that multiplying, what you do, you add the exponents. That's a way of turning multiplication into addition. And this is really what underlies, although Napier wouldn't have thought of it like this, what underlies the eventual development of things like logarithms. So, this innocent bit of initial progress that makes it a bit easier, but then leads to whole new avenues of thought. And actually, there's a quote I'm going to read you from Ernst Mach in 1895. He said, "The student of mathematics often finds it hard to throw off the uncomfortable feeling that his science, in the person of his pencil, surpasses him in intelligence." In other words, you come up with some bit of notation and then, or some new bit of exploration, and then you find that it's leading you off into all sorts of new places. It goes much further than you thought, linked with other bits of mathematics. So this is kind of an often thing, slightly disconcerting and wonderful thing about mathematics. Okay, now, I want to give you a little further anecdote about how the language we use for notation and symbols can tell us about where that mathematics has come from. So we've seen with our numbers, they started in India. Another thing that started in India was, trigonometry. So where does this word sine come from? It's a lovely story, and this archer is going to tell us the story. So the Indian mathematicians who were writing in Sanskrit, they wanted to explain what they meant by sine. So we know sine in a triangle, it's opposite over hypotenuse, right? The sine of that angle. So if you imagine here this guy, imagine this being an arc of a circle. It's not quite, but it's pretty much. And there's his bowstring there. And then when he pulls back to fire an arrow, we get a drawing a bit like this. And this angle here, what's the sine of that angle? It's the opposite over the hypotenuse. So the opposite bit is this bowstring, right? Or, half the bowstring. And so if you have that diagram in mind, it's really natural that the word for sine was the word for bowstring. jiva in Sanskrit. My pronunciation is not guaranteed to be correct. So this is how it first started. And then, just as with the numbers, these works found their way into the Arab world and were translated, but there was no word for sign in Arabic. And so what happened was they used the word jiva, which didn't have a meaning in Arabic in its own right. It now just came to mean sign, and it became jiba in Arabic. So that isn't a word already in Arabic. And so then what happened was it was a bit sort of corrupted over time into something that was a word. And that word was jabe, which means cavity. Okay, so then fast forward a little while, the Arab texts come to the Western world and get translated into Latin, and now the word cavity is translated into Latin. What is that? In Latin, it's sinus. Like we have sinuses, in our skulls. We have a sinus. And so then in English, that's sign. Right, so this is this word, and you can see originally the lovely bowstring analogy, and it's travelled across all these languages to get to us, which is just a nice story there of some of these trigonometric terms. Okay, we've got about 10 minutes left. I want to briefly mention Robert Record again, because I said I would. He's a great guy. He's a Tudor, working for the Tudors, born about 1510. He was a big proponent of explaining things clearly so people can understand them. And he wrote in English, he wrote in the vernacular, he didn't write in Latin. He wrote several books. The one we want to talk about is called The Whetstone of Wit. It's how to sharpen your wits by doing algebra, which is always a good plan. But he had views about the importance of explaining things so that people who are in charge of making the rules actually have a basic grasp and understanding of science and mathematics, which we probably all can agree with still being a challenge. So he's said, "Oh, in how miserable case is that realm, where the ministers and interpreters of the laws are destitute of all good sciences, which are the keys of the laws. How can they either make good laws or maintain them that lack the true knowledge whereby to judge them?" Yes, indeed. So he then, in his book, The Whetstone of Wit, he was explaining in English for the first time, really, a lot of these rules about the Cossack art, algebra, how to take square roots, how do we understand about powers and things like this. He brought a lot of words into English. So he was reading books by Seifel and Rudolph that we mentioned. He read French, Latin, German, Italian, Greek, bit of Arabic. He was very widely read, and he brought words that he thought chose the best words from all these things. He brought them into English, and if there wasn't a good word, he made a word. So he gave us the words binomial and commensurable, for example. I can't quite stop myself mentioning some words that didn't stick. So what do you think these words mean? Well, absurd numbers, that's what he called negative numbers, still the old prejudice, they're absurd. Gemeaux lines, so that has the same root as Gemeaux or Gemini, twin lines, that means parallel lines. And his decision about calling the equal sign as a pair of parallel lines, he said, these are because no two things can be more equal than two parallel lines. So that was why he, when he wrote in The Whetstone of Wit, I'm going to use this sign, this is why he said he'd chosen it. No like triangles, we call them scalene now. None of the sides are alike. And syncangles, I like this one. Syncangles, that's pentagons, for obvious reasons, I guess. He also had a brilliant bit of notation that I want to tell you because it holds the record in the Oxford English Dictionary for the word in English with the most Zs in it. So here we go. So remember we had zensus earlier, meaning the number. So zenzica means the square. And zenzizenzica, obviously then, means the fourth power, the square of the square. So then, of course, we have zenzizenzizenzica, which is the eighth power. And, take a big run up, zenzizenzizenzizenzica, which means the 16th power. So those are lovely, and I think we should bring them back into the classroom immediately and find the zenzizenzizenzizenzica of things. So those are some words that perhaps didn't catch on. But, of course, his legacy is the equal sign. That's what we remember him mostly for, this young man from Tenby. And I say this is the world's oldest equation, right? Why do I say that? I mean, of course, people were doing algebra. I'm not saying that, people weren't solving things. But what's an equation? It's something equals something. You can't do that if you don't have the equal sign. So this equation, this was the first use of it in his book, The Whetstone of Wit, 1557. Here it is. So if you can solve this, you can tell all your friends and family that you have solved the world's oldest equation. This symbol is the unknown. We'd now write x. This just means the number so a constant. So translated, we'd now write this as 14x plus 15 equals 71. So I'm sure you have solved it in your head already. If we just bring the 15 over to the right-hand side, take it away, we get 14x equals 56. And so x is 4, which I like because 4 is my favorite number. So this, we can, I'm saying this is the world's oldest equation. So that's Robert Record. So I wanted to finish this part before I spend like 5 minutes right at the end with just a little bit of mathematical fun with language. I wanted to mention just a couple more symbols you might be interested in. And to make the point, it changes and it often takes time for a choice to be made, a convention to be established as to what our symbol is. So these symbols here, these 5 symbols, were all used before 1930 to represent a particular number set. And that number set is what we now call Z. It's the integers, so the whole numbers. That Z for Zahlen, which is the German for number, that was chosen by a group of French mathematicians in about 1940. They got together and decided they wanted to have a series of books that were going to describe the elements of mathematics, and that's what the series was called. And they wrote individually, anonymously, but under the pseudonym Bourbaki. So these are very influential books, and they said it's high time we have a symbol for this that we all agree on. And this is the one they chose, and this is what stuck. So again, only in 1940. It feels like it's been around forever, but not actually within the last century it was finally chosen. Another thing is, I want to mention this wonderful equation. So this is often cited as the most beautiful equation in mathematics. It combines the very basic building blocks of number, 0 and 1. It combines pi, a very important mathematical constant, e, another very important mathematical constant, and I, the square root of minus 1, with which you can express the solution of any polynomial equation. These things, there's no reason to imagine they would be linked together, and yet they are with this beautiful equation. So this is a fantastic equation. So when did we get these symbols, e, I, and pi? So, Johann Christoph Sturm in 1689 was the first to use a letter for the well-known mathematical constant. Now, he used E, but the well-known mathematical constant he was using a letter for was what we now call pi. So I love that, because the first letter used for pi was actually E. And what was the first letter used for E? It was B. So if we were to follow historical precedent, this equation would be written b to the IE plus 1 equals 0, which just looks very strange to our modern eyes. So we don't always use the first bit of notation for things. Just to go back to this, what we now use, I want to sort of point out that, this is a beautiful equation. It belongs to the whole world. If we were to try and pick out which nationalities, like its DNA, well, E and I, they are due to Euler, who was the first to use those letters for those those quantities. Equals, that's Robert Record, he's Welsh. Pi was first used by another Welshman, William Jones, in 1706, I think. It's the first letter of the word periphery. And plus, we've seen that's a German origination, and then 0 and 1 are Indian. So you could say, this is 28% Swiss and 28% Welsh, 28% Indian, and 14% German. But of course, we don't do that. Mathematics belongs to us all, and this equation is 100%. It belongs to mathematics and to everybody. So, we obviously can't talk about every symbol, but I hope I've shown you a few of these. I just want to spend a few minutes now at the end being a little bit frivolous. It's my last lecture of the year. I want to give you some homework to keep you going until my next lectures start up again in October. So, I'm going to tell you what the incomprehensibility graph is. It's the kind of thing that gets mathematicians a bad name, but it's a bit of fun. Which languages are the hardest? Very important question if you're learning languages. So in English, we have an expression. If we don't understand something, it's Greek to me. It goes back to Shakespeare. But if you're French, things aren't Greek to you. They're Hebrew to you. That's first quoted, I think, in Molière. So obviously, this means that Greek is harder than English, but Hebrew is harder than French. And you can start making a graph of this. A directed graph, so you have an arrow from a language to the thing that it doesn't understand. Okay, so we can start doing this thing, and we can try and find out what are the hardest languages, or is there a unique hardest language? So we've got our English and French going to Greek and Hebrew. Stumbling block, potentially. English, we can also say, if we don't understand something, it's double Dutch, right? We don't understand it. So we also ought to have an arrow to Dutch. But it turns out not understanding Dutch is really just a stepping stone on the way to not understanding Greek, because the Dutch don't understand Latin. And if you're in Latin, you can say, it can't be read, it's Greek. So actually, we end up at Greek both ways. What about Hebrew? Well, both Greek and Hebrew don't understand Chinese. So we get to Chinese. And what does Chinese not understand? Well, there's a lovely expression, heavenly script. It's heavenly script to me. So the writing of heaven is the ultimate incomprehensible language. Now, I've put something in the transcript about this. There are people who have drawn much bigger graphs and taken this much further. You can explore this idea further if you wish, but it's quite a fun idea. Not really mathematical, but it sort of looks a bit mathsy. Another mathsy thing, which I've called numerolinguistics. What's the next number in this sequence? 84, 11, 6, 3, 5. If you're watching this lecture on recording, you should pause this now and do your due diligence and try and work out what the next number is. For us, here it will help you to see the words written down in English. So let's look at this. 84, E-I-G-H-T-Y-F-O-U-R. 11 characters are needed. 11. How many letters in 11? 6. How many letters in 6? 3. How many letters in 3? 5. So the next number is, how many letters in 5? 4. How many letters in 4? Oh, it's 4. That's interesting. It's 4 again. Ah, my favourite number is 4. Of course, it's fate. Let's try starting at a different point. So there you can start with 84, you get to 4, and then you're in a loop. If you start anywhere else at all, any other number, you end up at 4, and then you're stuck. You stay there. So we can draw another kind of graph, the graph of English, following this pattern. It's, a function of the number. It's the number of characters required. I'm counting hyphens. I don't count spaces. That's my rule. You can make your own rule if you prefer. You end up in the same place. You end up at 4 with English. Well, there are lots of languages. This is the graph for English. Everything is 4, the best number. In Italian, all roads lead to tre. The word for 3 has 3 letters. In Danish, there are 3 numbers like this. There are 3 fixed points. 2, 3, and 4 all have that respective number of letters. Now look at French. This is brilliant. So un has de letters, and de has quatre letters, and quatre has six letters, and six has trois letters, and trois has cinq letters, and cinq, 5, has quatre letters. We've got a cycle. It's fantastic. So in French, there aren't any fixed points, there's just a cycle. Now, so your homework is going to be take some languages you like and that you know, or even that you don't know. What happens in your favourite language? Now, point of caution, how far up do you have to go before you've captured all the behaviour? Can you, for example, go to one of the many websites that tell you all the numbers in different languages from 1 to 10? Is it safe to stop at 10? Glad you asked. No, it is not. Одиннадцать in Russian, that's the Russian for 11. It has 11 letters. You can't stop at 10. So be careful, you might need to go up a bit higher. So here's your homework to keep you going. What's a safe testing threshold? I've been going up to 100 in the languages I've looked at. That seems to be pretty safe, but what's a good place to stop? What's the highest fixed point? So 4 is a fixed point in English. You always get back to 4. What's the highest one you can find in any language? Is it 11? I'm really unsure whether anyone is going to be able to tweet me saying they can beat Zulu. Because in Zulu, 27, as of course you know, is Amashumi Amabili Nesikumbisa. That has 27 letters. Can you beat that? I don't know. Maybe you can. And then can you find a longer cycle than the one we found in French that has 4 in it? So that's a little bit of fun to keep you occupied until my next lecture in October, which is on mathematics and art. And then my second year of Gresham lectures, the first few lectures are going to be on the many, many links between mathematics and art. You can watch all the past lectures. You can sign up for upcoming ones at the Gresham website. Or if you follow me and Gresham on Twitter, of course, we'll let you know about upcoming events. But I will stop there. Thank you very much for listening.
Professor Hart, thank you very much for a really, really interesting lecture. We've got a few questions from the online audience.
Sure.
I'm not going to be able to get to all the questions, but we will try. We'll try to do as many as possible. Okay. I read somewhere that when we were trading with other countries in the world by sale, mathematical puzzles would be exchanged with various mathematicians because even though they couldn't speak the other's language, they could all understand the maths symbols. Is that true?
Well, so I think we've seen that there have been lots of different symbols used over time. It had helped, of course, that for a long time, learned people would speak or write in Latin, so that helped people of different nationalities communicate with each other, certainly within Europe. There are examples of puzzles and games that you see in different places, even if we can't necessarily trace the pattern, we don't have records of them travelling, but there's a puzzle about 17 camels, for example, that crops up all over South Asia, and this has clearly been passed on between people. So I think that has happened, but probably, various languages that have been the lingua franca at various times have helped with that, yeah.
Okay. We do time in base 60. Is that related to the Babylonian system?
It absolutely is, yes. So the Babylonian system with base 60, it wasn't just the counting system. Their currency was measured in 60s, and it came from the kind of 360 days-ish in a year. Now, the Babylonians were much better astronomers than anyone who would think that they really were 360 days, but what they said was there kind of had been 360 days, and then in the ancient world there were various myths about how those extra few days came in. So the ancient Egyptians had a myth that the sky goddess won those 5 extra days in a bet with the moon god Khonsu, and so there were 5 extra days, but they somehow were extra intercalary days and were not part of the months of 30 days. The 60ness and the 360 days in a year, which of course also gave rise to our 360 degrees in a circle, which we still have and divided into each degree into minutes and seconds. 60 is a great number because you can divide it up in so many ways. It's the smallest number that is divisible by 1, 2, 3, 4, 5, and 6. So that makes fractions much easier. You're much more likely to find a fraction that doesn't, that exists than in our base 10, where even a third is very difficult to write, as a decimal or something. So 60 is a good number, but it does go back to the Babylonians, yeah.
Great. I've got another person who's saying numbers of quantities are our first record of numerical symbols, the purpose being to levy city tax on goods for sale. Is this true or false?
Oh, golly. The first ever records. The honest answer is I don't know the first ever. And we probably won't know because things are being dug out of the ground all the time. But certainly I have read that even the earliest writing at all is numbers. So these things are there right from the off. Even if it's just making marks very simply, crudely, 1, 2, 3, 4, 5, just marks in a piece of clay, they are really with us right from the beginning of any kind of writing, yeah.
You spoke at the beginning of the lecture about Voyager. Were the plaques on the NASA launches in forms other than audible/visible to humans? So
they were put onto a record. And so you can put information onto a record. If you have I guess the most recent bit of technology might be the CD that still does this. And there were instructions put onto that golden record as to how it was to be used. And the very first picture was just of a circle, and that would allow you to realise you were doing it right, because of course, a random bit of thing is not going to be a circle. So every civilization would recognise that. So there were instructions on how to read it, but it was a record. Yeah, so it had music and pictures.
Okay, this is a big question. Are mathematical symbols free of white colonialism influence? Hopefully, yes. But in case they are not, what would be the alternative way forward?
That's a really great question. I think usually over time we have, converged on eventually the best, the thing that's convenient, the things that are most powerful, that exponent notation, that makes sense and it works. And it can take time. And I think what can happen is that things are misnamed. And so you saw, the Arabic numerals were really Indian numerals. I've seen other examples where, so I remember reading about this Nigerian mathematician in the 18th century, Ibn Muhammad, I think his name was, and he came up with this method for constructing magic squares. But we don't know it by that name. It is now known as, and I don't like this really, but I read about it as being called the Siamese method, so from the ancient, the old word Siam, for modern day it's Thailand, isn't it, Siam now? But it was because this method was not really paid any attention to until this French diplomat who happened to be in Siam found out about it, and he wrote it down, and so then it's called the Siamese method, right? But, those kinds of things where things are mislabeled according to the dead white guy who wrote them down because he got them from someone else, we've got to be careful about those things. So I think ultimately, probably the best symbols win out, but we have to be careful about who we credit them to, and that's why it's really important to study the history of these things.
There's another international question. How did South American civilizations count? Is this the topic of another lecture?
Yeah. So I did not talk about the Chinese methods, the Japanese methods there. So I have got quite a few links in the transcript, and there are some good books about this topic. But I don't want to make a mistake, but I believe there was a base 20 system that was used, so not base 60, not base 10, but base 20, and that's a very interesting and quite sophisticated counting method or number system. But sheer crunch of time, I thought I had to refine it a little bit. But all over the world there were counting systems.
Here's another interesting one. Why was our old money system not based on 10, but on 12 pennies in the shilling and 20 shillings in the pound?
So I think the 12ness, it's the same thing as for 60s. It's much easier to divide 12. 12's got a lot of factors, so you can have half and a quarter and a third. We have had threepenny bits and things like this, so you could divide up a shilling into many more things easily than you can divide 10 pence up into, or 5 pence. So that was, when we were doing all our arithmetic in our heads, that made life much easier. As it became less important to be able to do everything in your head, when we had cash registers and things, that motivation for dividing things into 12 lessened. So that's probably why we switched decimal eventually,
That's really interesting. And another money question. Which culture assigned money symbols, the euro, the pound sign, the dollar sign, to numbers? Where did that begin?
So having those signs, they will have come in, I guess, if you're just within your own culture, what money you're using. But as soon as you start trading with other cultures, you need to say, what am I measuring? So I know there's a long discussion on the dollar sign in Florian Cajori's book about mathematical symbols. The pound sign comes from the Latin word for pound, libra, right? It is an L, so it's a sort of deformed L, our pound sign. Euro is obviously to do with Europe, so it's an E. So these things do develop, and they need to develop when you've got, imagine being in a market and someone's writing how much things are in dollars and how much they are in pounds, how much they are in francs and lira and all of those kind of things. You need a symbol to say what money you're using.
Professor Hart, thank you so much, and thank you for your generosity in addressing the questions. Thank you to our audience for attending, and I would like to encourage you to come back tonight and listen to our Professor of the Environment, who will be giving a lecture at 6 p.m. called A Just and Rights-Based Framework for Nature. So we hope to see you later on. Thanks very much.